now it's our great pleasure to have a talk by Professor Seiji Yunoki from RIKEN. So before going to talk, I would like to briefly introduce his research histories. And Yunoki-san got his PhD from Department of Applied Physics, Nagoya University in 1996. And after doing postdocs in European and European countries and United States, he came back to Japan as a research scientist at RIKEN. Since that time, he has been conducting computational condensed matter theory group in RIKEN. And also recently, he is very actively doing researches on some condensed matter theory application of real quantum computer. And I think that Yunoki-san's group is one of the most active research group on this direction. And today his talk is also in this line, and which probably I hope that his talk is attract much attention from the audience of this colloquium. So Yunoki-san, please start.
Yes, thank you very much for a very kind introduction. So what I would like to discuss in this talk is our very recent research on quantum many-body dynamics using digital quantum computers. In this regard, we put two papers in the archive. One is the quantum dynamics simulation, quantum dynamics experiments using IBM superconducting quantum computers, and the other is the quantum many-body dynamics using continuum trap-down quantum computers. And since I somehow figured that I have enough time to explain both of them, I would like to focus on the research reported in this first paper using IBM quantum computers. So before going into the detail of our research, I would like to spend several minutes to introduce quantum activities that is going on in RIKEN. So RIKEN, the main campus of RIKEN is located in Waco, and we have started research center for quantum computing and quantum information led by Professor Nakamura. The research center is called RIKEN Center for Quantum Computing since 2021, 3 years ago. And Professor Nakamura and his team released first domestic quantum computers having 64 qubits last March. The name of this quantum computer is called A. And in this research center, we have many other distinguished researchers, like both in experiments and theory. For instance, we have Professor Fusawa, who is, of course, a leading researcher in optical quantum computers. And also we have Professor Tarucha. He has excellent work doing the silicon-based quantum computers. And in the theory side, we have also Fuji-san. Of course, Fuji-san is a professor in Osaka University, but he has also a research team in RIKEN doing theoretical study. And also we have Frank Nori and Daniel Ross and others, including myself. And in Kobe, of course, we have HPC, classical HPC computing center, RIKEN Center for Computational Science, led by Satoshi Matsuoka. And there we have supercomputer Fugaku, was the fastest supercomputer in 2020 and 2021. And it's still our fourth fastest supercomputer around the world in the latest ranking. announced this May. And also, Fugaku is ranked first place in several other metrics. And April of 2022, Professor Gonokami, who was the former president of University of Tokyo, took the president position in RIKEN, and under his leadership, we have started RIKEN internal project, TRIP project, transformative research innovation platform of RIKEN platforms since last April. And one of the project in TRIP project is to construct a quantum HPC hybrid computing system, literally connecting supercomputer Fugaku, that is of course located in Kobe, and quantum computer A, located in Wako campus. And we have successfully done POC type proof of concept demonstration connecting supercomputer Fugaku and quantum computer A this May in collaboration with the Osaka University. And the application side, we started a sort of a virtual platform or virtual organization called RIKEN Quantum. And RIKEN Research Center ISEMS. And the idea of RIKEN Quantum is to simply promote quantum computational science for basic researchers, basic research in different research fields, including, of course, physics, chemistry, biology, and also we are trying to include the humanities. And already more than 15 PIs, 16 PIs in exact, get together to apply quantum computing to each research field. And we have non-PI researchers in RIKEN Quantum, like 10 researchers already. And also we have two distinguished collaborative researchers. Professor Nomura is a professor from University of Berkeley, and Professor Ozawa is the professor in Chubu University, and they are also kindly joined these activities with us. And in RIKEN Quantum, we are still looking for researchers in different levels, including postdocs, which will be a 3-year position, research scientists for 5 years, and also we are looking for senior research scientists, which will be like a 7-year position. And also we are calling for a RIKEN Quantum collaborative researchers proposal. And with this call, we would like to offer an environment to use quantum computers for fixed-term young researchers outside RIKEN through this proposal. Although the deadline has already passed, we are still accepting applications in this call. And another important project that we have started since last December is what we call the HPC Quantum Project, funded by NEDO, and the project leader is the Mitsushita Sato from RCCS in RIKEN. And in this project, we will implement 2 quantum computers. One is the continuum trapped ion quantum computers that will be located in the main campus. RIKEN at Waco. The other is the IBM quantum computers placed in Kobe, just next to Fugaku, and to construct quantum HPC hybrid quantum platform connecting these two quantum computers and supercomputer Fugaku, as well as supercomputers in Osaka University and the University of Tokyo. And the goal of this project is to construct quantum HPC hybrid computing platform by April 2026. And by the end of this project, we would like to prove the effectiveness of this platform through practical applications showing quantum advantage, whatever the definition might be. And with this project, we are also trying to hire several researchers in different level. And I would like anyone who might be interested, especially in quantum HPC hybrid computing, to apply this position. Okay, now coming back to the main context of the presentation. The main question that one might have is what is the best use of noisy quantum computers that are available currently? And in the field of condensed matter physics, since I'm from the condensed matter physics, probably the best use of the noisy quantum computers is not for any computational tasks, but use the other digital quantum simulators. So we just use them to do some experiments, quantum experiments. So in terms of using quantum computers as the digital quantum simulators, one of the pioneering work is the quantum dynamics experiments done by IBM in this Nature paper published in last year. And there and here they are trying to claim that the limitation, they can reach the limit of the classical computing by using quantum computers. So what they did in this Nature paper is they did a quantum dynamics of two-dimensional transverse field Ising model using 127 qubits. And trying to show that this dynamics can be very difficult to treat using classical computers. So another reason that I want to show this is because one of the authors in this Nature paper is our postdoc, Yantao Wu, who his contribution in this paper is he did classical simulations using tensor network methods. So in this Nature paper, what they did is they did the Floquet dynamics in the transverse field Ising model or kick Ising model. So they consider two-dimensional transverse field Ising model on a heavy hexagonal lattice. They considered this two-dimensional heavy hexagonal lattice because their qubit geometry is exactly in this form, this heavy hexagonal lattice. Here, the circle indicates the each superconducting qubits. And this bond denote the connectivity of two qubits, neighboring two qubits in their device. And they studied the Floquet dynamics, starting with a fully polarized state, like fully, they all spins are aligned in the up direction, for instance. And the Floquet unitary of single circuit, or UF, is composed of two terms, exponentiated ZZ term, which is a 2-qubit ZZ rotation that generate quantum entanglement in the quantum state, and also a single qubit X rotation gate, which is nothing but a single qubit rotation around the X, around the X direction, which is represented by 2x2 matrix shown here. And the 2-qubit ZZ rotation gate is represented by 4x4 matrix. And generally, this ZZ rotation gate requires two C0 gates. But tuning the angle theta of the DD rotation, one can only describe these DD rotations using single C0 gate, and they fix this angle theta at this particular value, pi minus pi half. So they did this because it's very important to reduce the number of 2-qubit gates in the quantum circuit, because 2-qubit gates is responsible for making a lot of quantum noise in the quantum circuit, and therefore one wants to reduce the number of C0 gates in the circuit. So, using fixing this angle theta in the ZZ rotation gate, they did this Foucault dynamics up to 20 time steps or total steps, if you like, on this heavy hexagonal lattice shown here. And remember that when theta h, which is a rotation angle, a single qubit rotation angle along the x-axis, this theta h is 0. This is simply a classical limit, because provided that initial state is the product state in computational basis, like in this case. And when the theta h is by half, all that circuit can be represented by a set of particular gate called Clifford gate, which is also a simulatable classically, very efficient in the polynomial time. And just looking at the entanglement entropy when you divide a system into half, one can really find that 20 time step is enough to reach almost maximum quantum entanglement that you can have in this dynamics. So in order to have, in order to obtain any meaningful observations, average value of expectation value, one also has to do error mitigations to mitigate errors in the observable. And they did several different error mitigation techniques, including readout error mitigations, and also Delonoid extrapolations associated with probabilistic error amplifications. For instance, this is the example for the Delonoid extrapolation with probabilistic error amplifications. So essentially, the level of noise can be parameterized by parameter G here. And when G is 1, this is the unmitigated circuit. and 0.2, 0.6 implies that the noise level in the circuit is increased by 20% and 16% by introducing, for instance, redundant gates in the circuit. The idea of this zero noise exploration is simply by increasing the noise level and do the measurements of this expectation value, in this case, the magnetization at some particular qubit, and extrapolate these values to noise level 0, which is supposed to be the pure ideal limit. And they found that by using the exponential extrapolation instead of linear extrapolation, they find a reasonable value very close to the expected value, which is 1. In this case, theta 8 is 0, and therefore we know that the exact value should be like 1 in this case. And they did the similar experiments to check this error mitigation method for different total steps n up to 20. And here, this green circle is unmitigated raw data, raw experimental data, and the blue circles are the experimental data after error mitigation. One can see that these values after error mitigations gives you reasonable values that is close to 1 within like 5 to 10% of error. So using this error mitigation method, they did very systematic calculations varying the value of theta h. Again, theta h is the rotation of a single qubit rotation angle from 0 to pi/2. Here is the average of magnetization. Here is the average of 10 power strings, and here is the average of 17 power strings. And these blue circles are raw data, raw experimental data, and these blue circles indicates the experimental value after error mitigations. And these solid lines are the exact result, since these expectation values can be evaluated exactly. And you can see that the expected values after error mitigations are in good agreement with the expected values, exact values. On the other hand, if they do MPS calculations with bond dimension 1000 and two-dimensional tensor network calculations based on the isometric tensor network with bond dimension 12, they found that although that they can reproduce these exact values when theta h is small, because theta h0 is the classical limit, and one would expect that the entanglement, quantum entanglement, is small when the theta h is small. However, away from this limit, the agreement becoming worse, and even their MPS calculation or tensor network method, it was completely wrong when theta h is close to pi/2. This already implies the difficulty of calculating classically based on a tensor network-based method in these parameter regions. And they did also another set of experiments calculating the averaging the 17 Pauli operators for time evolved state up to like 5 times steps, and they found after mitigation these are the estimated values after error mitigations. And since we know that when theta h is by half, this value should be 1, and indeed their estimation is very close to the expected value here in this limit. And when they use MPS method with bond dimension more than 3,000, also considering the light cones of this dynamics, they were not able to reproduce these experimental results. And also they did they measured single site magnetizations for the 20 times stepped state. And these are the raw data. And this blue is the obtained result after error mitigation. We can see that MPS and the 2D tensor network method can successfully reproduce the experimental value when theta h is small, where the contact entanglement, loss of the contact entanglement is expected to be small. Whereas when theta x is large, the classical simulations failed to reproduce the experimental value here. And with this, they claim that the quantum computer provides correct results for which leading classical approximations such as 1D and 2D tensor network methods break down. So this Nature paper is published in last June 14th, and almost 2 weeks or less than 2 weeks later, one paper came out by the researcher from Flatiron Institute, claiming that their tensor network method based on brief propagation can reproduce the experimental results very reasonably. And 2 days later, even 2 more papers came out by Google and Caltech. They are also claiming that the experimental results can reasonably reproduce their calculations based on, for instance, tensor contraction method and Clifford perturbation theory-based method. For instance, this is the results by Flatiron Institute. They did tensor network calculations based on brief propagation. And indeed, they found that their calculation, which is indicated by this blue dot line, can reproduce IBM experiments, which is denoted by circle with error bars. Yes, also Google can show us that their experiments can be reproduced by their classical simulations. And even more papers in 2 months later came out and claiming that classical calculations based on tensor network method, both the tensor network method, can reproduce IBM experiments. And another papers based on, again, the tensor network method, also claiming that IBM experiments can be reproduced using classical calculations. Okay. Although the claim of going beyond classical limit might be wrong, I believe that they are very happy with these classical calculations, because at least those classical calculations confirmed that the IBM experiments is really correct. And they think that their achievement published in this Nature paper is one of the milestones, saying that the noisy quantum computer is able to produce accurate expectation values on 127 qubits, that is outside of a brute force classical computations. By brute force classical computation, they mean state vector method. This is essentially a numerically exact method. And the most advanced state vector method can treat slightly less than 50 qubits if one uses, for instance, all node of Fugaku. So, by the way, this view graph is presented by Jay Gambetta. Jay Gambetta is the top of the IBM Quantum in IBM Quantum Summit last year. IBM Quantum Summit is one of the most important events organized by IBM, where they announce their achievements and new roadmap and new quantum devices. And in this presentation, he also claimed that we have entered the era of quantum utility. And indeed, after their Nature papers, 6 papers by the time of this quantum summit, which is held in last December, 6 papers came out using more than 100 qubits. For instance, for this study, they did ground state preparations. And here it's basically a quantum dynamics. And here, study by Keio University and University of Tokyo, they did quantum reservoir computing. And here it is more like ground state preparation or quantum dynamics here. And here is the ground state preparation for Schrödinger model. And here is the demonstration of decomposing long-range 2-qubit gate using measurement. So even he is like claiming that challenging us by saying that if you are not using 100 qubits, you are not doing quantum. So motivated by this progress, we also wanted to do something using more than 100 qubits, since we are also in the place of being able to use IBM quantum computers. And this is exactly what we did. We did like quantum dynamics simulations or quantum dynamic experiments using their quantum computers. More precisely, we studied a plasma discrete time quasi discrete time crystal and quasi crystals in 2-dimensional Klein system on digital quantum computers. And I would like to say that this is our paper is one of the first 2 applications using more than 100 qubits on the IBM Heron processor. And the IBM Heron processor is the newest quantum computer having 133 qubits available since last December. And the other paper is quantum simulations of hadron dynamics in the Schrödinger model using more than 100 qubits by the researchers in University of Washington. So Gambetta was so kind that he also make a statement in his SNS about our papers. So in the beginning, I said that one of the best use of current noisy quantum computers is not to do any calculation, but for use them as digital quantum simulations. But here, very recently, we did first applications for computational tasks using more than 70 qubits of Heron processors in collaboration with IBM. Even calculating the ground state of iron 4-alpha-4, which is known as very challenging molecules if you treat it using only classical simulations. And if you are interested in the application of quantum chemistry, please look at this paper. So what they did in this quantum dynamics simulations is as follows. In this study, we did the experiments of long-time quantum dynamics using 133 qubits for up to 100 time steps. Remember that the time steps that IBM did in their Nature paper is only 20 time steps. So we did it more than 5 times longer. And confirmed that the expectation values are reliable even in such large systems, large circuits, by systematically comparing experiments with classical tensor network simulations using Fugaku, and show how quantum computing can complement classical calculations. And lastly, we discovered a new phenomenon that is discrete time quartz crystals in two dimensions. So discrete time crystal is a non-equilibrium state with spontaneously broken time translation symmetry that is analogous to special translational symmetry broken state in equilibrium. And in the Hamiltonian or in the unitary operator that drive this dynamics has a discrete time symmetry, and the discrete time crystal breaks this discrete time translational symmetry. Typically, like a periodic doubling might be observed in this the DTC. And the periodicity of observable that indicate DTC, discrete time crystal, is robust without having to fine-tuning the model parameters. And observables should maintain its periodicity over a very long time in the thermodynamic limit. And therefore, the system must have a localized nature and had to be summarized. And the last conditions here is not really necessary when your state is a pre-thermal state. So of course, we are not the first person who studied this DTC using data quantum computer. So the pioneering work in terms of this DTC is the study by Google T using their device, Sigma device. And they studied one-dimensional systems with 20 qubits, and they introduced disorder to induce many-body localization. And there, the flow K unitary is composed of 3 terms, 2-qubit DZ rotation, single qubit X rotation as well as single qubit Z rotation, and they choose these parameters theta I and hi randomly so that you may have a many body localization. And when G is 1 in their parameterization, that last term is simply a proportional of the product of X operator, power X operator, and therefore trivial DTC is expected, provided that the initial state is a simple product state in a computational basis. And indeed, they found when G is very small, like 0.6, that is less than some critical value, the magnetization decays very quickly as a function of time t, or time step t, implying that this is the thermal regime or thermal phase. On the other hand, when G is very large, close to 1, like 0.97, they see this oscillationary behavior in the magnetization as a function of time steps. This is the one of the evidence that you have a discrete time crystal. And the less known work is the study reported in Science Advance paper done by 2 researchers from Australia. They use IBM quantum computers to study one-dimensional system with 57 qubits. And they also introduced a disorder to induce many-body localization. And their Fouquet dynamics is derived by this unitary operator composed of 2-qubit ZZ rotation and the single qubit X rotation. And they choose this JI randomly. And when epsilon is 0 in their notation, one would expect that the dynamics is simply a trivial DTC, again, provided that the initial state is a product state in a computational basis. And indeed, they found that when epsilon is very small, like 0.05, they find like this oscillationary behavior in the autocorrelation function. Okay. Even this behavior becomes more apparent when they did error mitigations proposed by themselves, showing that this oscillation is clearly continuous up to like 50 time steps. On the other hand, when epsilon is very large, like 0.5, this correlation function decays very quickly, even after error mitigations here, indicating that the dynamics is more like a chaotic thermal regime. Okay, and in our study, our focus is the 2-dimensional systems. According to a study in this paper, for instance, DTC can be induced either with or without randomness. With randomness, this DTC behavior is expected even with a short-range interaction in one dimension. That are the studies that I shown in the previous view graphs. On the other hand, pre-thermal DTC is also expected even without having any disorders in 2 dimensions or more than 1 dimension. So what I would like to also emphasize that there is no studies using more than 100 qubits in the context of this DTC, and almost no studies in 2 dimensions, and especially no experiments in 2 dimensions. And there is no study comparing with classical simulations, and we did all those in this paper. So again, our focus is on clean two-dimensional system, implying that classically more challenging. So we use the IBM computers, especially this IBM quantum system 2, with Heron processor, which is the newest quantum computers available since last December. And the quantum computers that they used in this Nature paper by IBM is the IBM quantum system 1 Eagle processor, having 127 qubit, which is 1 generation old. Although, but just looking at the numbers for the characters of the bits and gates, one can see that indeed the 2-qubit fidelity is slightly better in this newest device, Heron processor, compared to the Eagle processor. On the other hand, coherent time T2 and the relaxation time T1 is slightly shorter than the Eagle processor. However, we noticed that the 2-qubit gate time is much faster in the Heron processor, like 4 times or 5 times faster than the Eagle processor. This is, of course, important because this implies that we can do a dynamics 4 times longer or 5 times longer, because relaxation time, we have to finish the experiment before the relaxation time or the coherence time. So we studied kicked Ising model or transverse field Ising model in 2-dimensional hexagonal lattice, having up to 132 qubits. And of course, our locate dynamics again are composed of DC rotations, single qubit X rotations, and single qubit Z rotations. And we choose 2-qubit rotation angles theta j at this particular value so that we can this 2-qubit rotation gate can be represented using only one Z gate. And therefore, we have 2 parameters, theta z and theta x. And in the Nature paper by IBM is focused on these parameter regions, whereas our study focused on this parameter region in the theta z, theta x plane. And again, when theta x is pi, this single qubit rotation operator is represented as simply a product of power X operator, and therefore one would expect that the triviality Tc is induced in this limit at pi theta x equal to pi. And our initial state is more like a stripe state. The quantum local quantum state indicated by white circles are all set to 0 or upspin, while the local state denoted by black circles are all set to 1 or downspins, and that would be our initial state. So I'll just skip this. And let's just look at how it works on Heron processor for small system size. So these 2 results are raw data, raw experimental data taken from from this 28 qubits indicated by this yellow line. And the left is the parameter at theta x is pi and theta z is pi half here. And the right corresponds to the theta x 0.8 here, and theta z is 0.5. And as I was saying, that when theta x is pi, one would expect a trivial DTCs where this magnetization oscillate between 1 and -1, and any decrease from this ideal value is due to quantum noise. And also this indicates that the fact that we have this meaningful signal even at time step 50 implies that the signal that we obtained in this particular parameter region is also real, although the signal is very small. And the question now is how we can mitigate errors. So the idea that we adapted is based on the fact that that when theta x is pi, the magnetization, the absolute value of the magnetization should be 1 when theta x pi, because it's the classical limit. And we use this to mitigate errors, assuming the global depolarizing model described by this quantum channel here. So with probability P, the quantum state is unaffected by noise, and probability with 100 is 1 minus P, the quantum state is completely destroyed. And the expectation value is represented by this form, and this one in the left is the measured value, and this one is the ideal value that is what we want to estimate. And knowing that the average value, the absolute value of this magnetization at theta x pi is 1, we can estimate this fidelity P at this particular value of theta x, because the trace of a Pauli operator is always 0. And we approximate this fidelity for other parameters, theta x, using the fidelity estimated at this value of theta x. And therefore, our mitigation protocol is very simple by dividing the expectation value by the expectation value measured at theta x is pi. So how does this work? So again, this is the left figure is the classical, the theta x is pi, which is the classical limit. And what I was saying is that to simply divide this value by the absolute value of this, which is indicated by crosses here. And this yellow diamonds is the estimated value after error mitigation that is compared with the state vector method, which is the numerically exact method. We can see that the agreement is excellent up to like 50 times steps. So this agreement is very significant because one can rarely see this much of agreement in any experiments using ideal quantum computers. And we also tried this mitigation scheme for 133 qubits and also found that the experimental value estimated by using this simple error mitigation scheme indicated by this yellow diamond it is very much agreement with the classical two-dimensional tensor network method with different quantity dimensions. So since I would like to be honest, I'm also going to show other results for different parameters over long time steps like L28. Here is the theta x is pi with varying theta z. And therefore, this is like a classical limit where you would expect trivial DTC behavior. And any decrease from this ideal value here is because of the noise. And here, the three are theta x is 0.9 with different value of theta z. And here, the threes are for the theta x is 0.8. And to mitigate the errors, simply divide these quantities by the absolute value of this measured value. And this yellow diamond is what we obtained after the error mitigations. And these squares are state vector method. So one can see that although some regions, the agreement is not that particularly good, but overall, the agreement is satisfactory, especially considering that we are doing simulations up to 100 time step. Okay, this is the same figure, but for up to 50 time steps. One can see that the agreement looks much better in this scale. So in order to understand the computational complexity, I would also like to compare MPS versus set vector for 28 qubits. We can see that when theta x is 0.8, which is very close to the classical limit at theta x pi, the MPS and the state vector method agrees quite well. However, when theta x is 0.8, which is slightly away from this classical limit, the deviation becomes apparent, obvious, especially when the time step is longer here. The MPS does not even converge even when we use bond dimension 5000. So for this purpose, we developed TBD method that is fully parallelized. And if you are interested in this method, please refer to these papers. And also, I would like to also compare two-dimensional tensor network method with a state vector method for 28 qubits. Again, when theta x 8.5, the agreement between two-dimensional tensor network and state vector method is perfect, whereas when theta x is 0.8, this agreement becomes bigger, especially when the time step is longer. Yeah, even the 2D center network with bond dimension 4,000 does not converge when the time step is as large as like 100 time steps, implying that this region is already computationally hard in terms of tensor network scheme. So in this tensor network scheme, we use basically a TDP procedure associated with trivial simple update. Okay, so encouraged with this agreement between theory and the experiment and the classical simulation, we did a very much systematic experiment varying parameters theta x and theta pi in this region. And already we find that when theta z is 0, we observe like this DTC, like periodic doubling oscillation, whereas when we increase the longitudinal field theta z, we observe longer period oscillations here, like a beating behavior is induced. And this is an indication of the discrete time quasi-crystal. So this behavior is more apparent when we do error mitigations indicated by this yellow or diamonds. Let me just skip this. And here is more like a DTC-like oscillation behavior. And here is a discrete time quasi-crystal like behavior. And this behavior is more apparent when we do a Fourier analysis of the signal. And one can see that when the theta z is 0, we see only a single peak appearing at 0.8, which implies that we have a periodic doubling DTC-like oscillations. In addition, when we increase the value of theta z, side peak are also induced with increasing the theta d, and this frequency is causing this beating-like behavior that we observed, and this is a sort of evidence of the discrete time quasi-crystal. So maybe let me skip this. So lastly, I would like to compare or experiment with the two-dimensional tensor network method for 133 qubits. And these trees in the upper panels for the theta x 0.9, which is close to the classical limit. And the tensor network already converges in this parameter region even up to 100 time steps. Whereas when theta x is 0.8, the convergence is not even achieved within this bond dimension. And comparing with this classical calculations, our experimental results indicated by yellow diamonds is a reasonable quantity. I mean, the agreement between these experimental and numerical calculations are reasonable, although the agreement is not perfect, especially when theta x is 0.8. We don't really know which one with experiment or numerical calculations are correct. So this is exactly the region where quantum computers is most valuable. Okay, let me just skip here. So summarizing this talk, using IBM quantum Heron processors, we have explored quantum dynamics of recognizing modeling in the two-dimensional heavy hexagonal lattice of 133 qubits for up to 100 time step, which exceeds previous studies in terms of qubit count and number of time steps. And we have observed that the pre-thermal DTCs and DTQC, discrete time quasi-crystal in two-dimensional green system on the digital quantum computers. And classical state vector simulations for 28 qubits and tensor network state simulations for 133 qubits confirm almost quantitatively that the experimental value obtained by the Heron processor is reliable, although error mitigation protocol introduced in our study is very simple. However, there is a parameter region where classical simulations are not yet converged with classical resource available, and this is precisely the region where quantum computing is valuable. Okay, thank you very much.
Okay, thank you very much, Yunoki sensei. Yeah, the current status of real practical quantum computation is very impressive to me. Anyway, now the talk is open. So is there any question or comments? If you have, please unmute your microphone and directly ask your question. Okay, let me ask one question. So in the DTC part, discrete time crystal part, probably the noise affect the amplitude of some oscillations. But as far as I see your figures, the noise does not so significantly affect the period of oscillation. And my question is this a general situation in the practical use of quantum computer, or is this a very particular phenomenon in this Kikuda-Ising model?
So I would say that this is more general, especially this usual DTC-like behavior. Because basically, like so-called these periodic doublings, so we have like up, down, like oscillations.
Yeah.
So the noise is usually decreases the amplitude of the signal in the project. And the period itself does not much affected by the quantum error.
So you can stably observe the doubling of period by using quantum computer. Yeah, that's fine. So thank you. So is there other question? Yeah, please.
Yeah, could I ask a question? So just on this last point about the classical simulation using tensor network. So I think you said that there is kind of a region where you think that like you get a different result with the tensor network compared to the quantum computer simulation. And I was just wondering, like, I mean, it seems like this might be quite dependent on the tensor network algorithm that you're using. And are you using the same tensor network algorithms that we used in that previous paper to simulate the system, or are you using some other algorithm?
So essentially this is the same algorithm.
Okay.
So yes, we in this particular calculation, so we use this so-called distributed simple update, but we also did a brief propagation method, and we found that essentially the calculation is exactly the same when the dimension is the same. Whereas when we use when we compare MPS and two-dimensional tensor network method, the difference becomes significant in some parameter regions. For instance, when theta x is 0.9, which is very close to the classical limit, the MPS and the tensor networks simulations agrees perfectly, essentially. Whereas when theta x is 0.8, these red indicates the two-dimensional like tensor network state method that we use with quantum dimension 3000, and these are the MPS result with different quantum dimensions up to 5000, and these differences are clear here, and this we believe indicates that essentially the difficulty or entanglement of the quantum state that grows in this parameter region, in this time step region, for instance. And
okay, thank you.
Yeah, concerning this experiment, of course, I'd say that the experiment is not really, not exact, but we cannot also say that the classical simulation is really exact in this particular region, for instance.
Okay, thank you.
Yes, thank you.
Okay, Takayanagi-san, please.
Thank you very much for very wonderful presentation. And I'm very impressed that this error mitigation is really improves the results in quantum computer. So this is a basic question. So you assume some model for error mitigation, but the result does not so much depend on the model you are assuming. Some kind of universality or some maybe some experience tells us that maybe that's not so important, or is that important actually?
So I would say that depending on the model that we use, actually. So
I see. So, but the result really qualitatively can be different.
So the truth is that we didn't try many different noise models because this is the first model that we tried, and it already works, and so we didn't.
I see. In this case, probably you know the answer, so you can probably choose the best kind of mitigation.
Yes, but in some sense we are lucky actually because.
I see. Yeah, but that's very interesting. Another question that in the first part of your talk, you also give us a plot of entanglement entropy and the time evolution. I think that's probably classical calculation. But yes. Do you get something similar also from quantum computer calculation, the read of some entropy?
It's not so trivial to obtain entanglement information from experiments. That's the problem.
But this plot is from actually quantum computer.
This is the classical answer. This is classical. I'm using Clifford.
I see. Thank you very much.
Yes.
Thank you very much.
Thank you.